Hello and welcome to section 19. In this video we'll be solving first order circuits that are powered with cosine inputs. So you can see example 1 here. We have a voltage source which is 4 cosine 2t. Initially it's turned off, but we're going to turn it on at time equals 0. We have a 20 ohm resistor and a 10 Henry inductor. So I've redrawn that over here. We've been asked to find I of t for t greater than 0, so after the switch, after it's turned on. And then our Vs, for t less than 0, it's 0. For t greater than 0, it's 4 cosine 2t. So to start solving this, because it's a forced function, we're going to need to get a differential equation. So let's go ahead and do that. We note that our energy storage element is an inductor. So its derivative form is V equals L di dt, and the corresponding equation for capacitor is V equal to I R. Again, you always want to get the form for the energy storage element that has the derivative in it, because that'll indicate what you want to do. So I want to add up voltages, which is a voltage loop. So let's do a KVL around I. Note that all of these elements are in series, so they share this current I. So I will get minus Vs plus 20 times I plus the voltage through the inductor, which will be L di dt, so 10 di dt, and it's I because that's the current through it. That's all equal to 0. We clean this up. So again, we want to get a leading coefficient of 1 here, so we're going to divide this by 10 so that we get a 1 there. I'll also rearrange at the same time. So di dt plus 2i equal to, so I'll move my Vs, because my Vs is my forcing function. We generally move those to the right hand side because they won't have the term I inside of them. So I will get Vs, and then I will get a 10 on the bottom. And using this form, we can then solve for the particular and natural responses. So recall that I of t is going to take the form I particular plus I natural. Because it is a first order linear differential equation, we know that this will take the form AE to the S1t, and we can look up here and tell that S1 is negative 2. So as long as it's a standard form, this should be minus S1 up here, and so minus negative 2 will give us a positive 2. So we know that S1 is equal to negative 2. For the particular response, for t less than 0, it'll be 0 because it's not being forced. For t greater than 0, it'll be a cosine function with the frequency of 2t. We don't know the magnitude, and we don't know if there's a phase shift, but we do know that it'll be a cosine function with a magnitude of 2t. It'll match that. So that becomes our challenge, is to find that particular response. So let's go look at t greater than 0 and find I particular. Now when we're finding I particular, we're trying to model the right-hand side as AE to the SPT. Currently, it looks like this. Vs over 10, where Vs is 4 cosine 2t, so if we rewrite that, we'll get 4 over 10 cosine 2t. So the reason we went over Euler's is because we know how to convert this cosine function into an exponential function. That's what we'll do so that we get, so this will become, so I'll simplify this down to 2/5. And then the cosine function becomes the real part of the exponential. Sorry about that. E to the j2t. So now we have the exponential form. And for the most part, you can drop off this real thing and just bring it back later. Just remember that's a cosine function when you convert back from the exponential. Our SP term is this J2 right here. J2 does not match negative 2, so we can do substitution. So we're going to set that equal to ddt, and we will do a substitution. So we're going to sub that again. This is our differential equation. We're going to sub it in here. So if I bring this back down, then I'm going to get a J2 times I particular. This was for the ddt, plus 2 I particular equal to our right-hand side, which we now have. So I'm going to make this 2/5 e to the J2t. So there is a real part on here, but I'm going to leave it off just to make the math look a little simpler. Cleaning this up, we get I particular, 2 plus J2. So there's that complex number that I was warning you guys about, equal to the same stuff on the right-hand side. Let's draw our triangle here. So we have the real part. We have the imaginary part. We draw this. So we have 2 in the imaginary, 2 in the real. So that means we know that theta is 45 degrees. And we're going to get that the r is 2 squared plus 2 squared, which is 4 plus 4, which is root 8. So when I rewrite this, I'm going to get square root of 8 e to the j 45 degrees times I particular equal to 2/5 e to the j 2t. So we wanted to convert this complex exponent, this into a complex exponential, so that we can then do our exponential math and get this down to a single term. So we're going to divide this over here. So we'll get I particular equal to 2 divided by 5 square root of 8. And then we'll get e to the j 2t. The 2t comes from here. And then we're going to divide it by the 45 degrees. And that's the same thing as subtraction. So minus 45 degrees. And then we're going to convert that back. So now this is just a number. And then e to the j 2t minus 45, we can turn this thing back into a cosine function. Because remember, we used a real operator, so we can undo the real operator now. So if you wanted to, you could write the real operator in. So 2 divided by square root, so 2 over 5 root 8 becomes 0.141. 1414, and then we're going to get our cosine 2t minus 45 degrees. So that is our particular response. So if I bring this thing back down, I now have that I of t is equal to 0.1414 cosine 2t minus 45 degrees plus a e to the s, which is negative 2t. So all I have left to do is find a. I know that this was initially not powered. There was no power initially, so that means that I of 0 minus was 0. It also means that I of 0 plus is 0 because it's through an inductor, and the inductor can't change current instantaneously. We have a di dt. So if you change current without changing time, you get infinite voltage. Again, just look at the form of the equation here. You can't have a change in current without a change in time. So we set that, and that becomes 0.1414 cosine of negative 45 degrees plus a. We solve for a. We find that a is 1/10, or 0.1. And we're done. I of t, we then 0.1414 cosine 2t minus 45 degrees, which is our phase shift, plus a 0.1 e to the negative 2t. And that'll be amps for t greater than 0. All right. Hopefully that helps. If you guys